So again, I'm David Pellerin, Business Development Principal for HPC in Amazon Web Services. I focus across industries, life sciences, manufacturing, aerospace, semiconductor sector. HPC means lots of things to lots of people. From my perspective, it means solving very big problems with lots of compute. Increasingly, that compute sits next to lots of storage. We'll talk about that as well, but we'll focus primarily on compute today. We'll hear about some use cases. I'll talk about categories of HPC applications, and then we'll dive into some of the best practices for performance of HPC applications on AWS. And then we'll turn to some of the new services that you've heard about this morning, the new instance types, specifically FPGAs. We'll talk about how those fit into the HPC landscape, and we'll talk as well about deployment methods on AWS for HPC apps. So first, let's kind of do a little bit of definitional work here. What is HPC? I mean, it means a lot of things to a lot of people. So when we think about HPC problems, as I said, we're really talking about very large amounts of compute. And that compute can be loosely coupled, it can be embarrassingly parallel types of workloads, it can be tightly coupled, legacy HPC. We'll talk about the differences in a moment. But some of the applications that we see migrating rapidly to the cloud, and we'll talk about why in a moment, are around simulations, right? Big simulations. Also things like deep learning training, remote rendering, these are all part of the HPC landscape, but increasingly it's those large-scale simulations that are moving to the cloud across industries. I wanted to talk about scale first, and about how researchers today in science are using the cloud for big compute as well as big data. This is the Large Hadron Collider. Large Hadron Collider generates an enormous amount of data every time they turn this thing on and smash things together. It's almost the definition of big data when they get all of this data flying out of this machine. They have to analyze that. They have to look for patterns, right? Back in January, there was some news that some patterns had been noticed in the data. I like this particular article. It talked about an unexpected bump in the data, which is almost the definition of big data. You're just looking for bumps. And in many applications, the bump itself, the pattern, the correlation is enough. It's actionable. That's all you really needed. But in big science and big engineering, to solve these real problems, that's not enough. You need to find causality. And that's where simulation comes in. So Brookhaven National Labs is one of the partners in the LHC projects, in the CMS project. And they run very large simulations. And they have a cloud portal that you can view on the Brookhaven site. And this is a snapshot of it showing what happened after that bump in the data in January. And what you're seeing in the green graph is as they begin to scale up on the cloud. And they're running stochastic simulations, Monte Carlo simulations, to try to get at the root of that observed behavior, to simulate it, right? Again, this is a grid application. It's a pleasingly parallel application. And you're seeing that on the cloud, using EC2 spot instances, they're scaling up and up and sometimes scaling back to zero. That might have been maybe somebody decided it was time to go home, or maybe they had to rethink the model, scaling down to zero, scaling back up. And at peak, they're hitting 60,000 cores for these simulations. And that's not an unusual scale anymore for customers in science and in engineering to hit those kinds of scales when they run big simulations on the cloud. In particular, if they can use spot instances, if they can run in a grid manner across availability zones, scavenge cores, if you will, where they can find them, they can do this very, very cost effectively on AWS. There's another interesting example that combines big data with big compute, and that's Fugro Roams. So Fugro is a large multinational energy company, and Roams is a division of Fugro that's located in Australia, and they do some really innovative work around managing infrastructure, power infrastructure. And their roots are in Australia, and you can imagine power infrastructure in Australia. It's a rather large continent without very many people. They're scattered all over the place. There's power lines that run everywhere. The infrastructure requirements relative to the number of people and organizations served is quite challenging. So what Fugro Roams does is they take aircraft, they equip them with high-resolution imagery, cameras, LiDAR, and they develop very complex 3D models by overflying all of this infrastructure. And that allows them to analyze potential risks. They can run simulations, right? So they bring the data in, they build a 3D model, now they run simulations against that. So for example, if a cyclone is going to come through, they can model the path of the cyclone, the wind speeds, and simulate the potential damage of that event. Pre-place assets, strengthen the assets, whatever they need to do. And this has saved them a tremendous amount of money. So it's a great example of big data analytics, rendering, right, types of applications, plus those big simulations. Another example is Western Digital's HGST division. HGST develops disk drives, very high density, modern disk drives. These are helium-filled devices. They're extremely dense in terms of the magnetics. HGST, to develop such a product, in particular the head designs, they have to run lots and lots of simulations, parametric sweeps. They also use the cloud for this, and at similar scales, actually. They're scaling at times to 85,000 cores to run these large-scale engineering simulations. So again, these are pleasingly parallel jobs. They are easy to scale out across many, many instances, taking advantage of spot instances in particular. But I'm going to turn and talk about more legacy HPC applications, more tightly coupled. In the area of fluid dynamics simulations. Now, fluid dynamics are different from pleasingly parallel applications in that they do require interconnects. Typically, they use MPI, message passing interfaces for those interconnects. They rely on things like placement groups on AWS and enhanced networking to make that feasible. And we are finding if you do tune properly, and I'll talk about some of those best practices in a moment, that you can get excellent scalability even of legacy applications like fluid dynamics. This particular case is star CCM, a benchmark example. And the scalability is quite good. It begins to drop off at some point, as any tightly coupled problem will. But if you use proper methods of domain decomposition with your CFD models, you can get outstanding scalability, in many cases to thousands of cores. So let's back up a little bit and let's talk about the landscape of HPC applications. One way to characterize HPC applications is in a four-quadrant grid like this. The vertical axis of this would be its need for tight coupling, right? So on the bottom would be your grid workloads, your embarrassingly parallel or pleasingly parallel workloads that can be scaled perhaps even globally. As I said, scavenging cores to run these simulations that are often independent. Good example would be a Monte Carlo simulation being run in the financial sector or in engineering for risk analysis, right? You can scale that out quite dramatically. On the upper end of the spectrum would be those tightly coupled legacy HPC workloads. So think weather simulations, fluid dynamics, impact simulations. They typically rely on message passing. They are very network intensive. Scaling of them requires you have close placement, that you have high performance networks between them. And so there's a whole range of applications in between, of course. The horizontal axis would be data intensity. So if you're going low and to the left, those are pleasingly parallel. They don't require a lot of data. Something like, as I said, a Monte Carlo simulation in finance, where you're just throwing random numbers at the problem, generating some data, and pushing it back out. If you move to the right, but stay on the lower sector, now you're into very data-intensive problems. They're high throughput from a compute perspective, but they do require a lot of data. Genomics processing is a great example of that. Animation rendering, great example. Semiconductor verification, right? Move high and to the right. These are the big iron, heavy-duty HPC applications that are both data-intensive and are compute and interconnect intensive. Now, increasingly, what we're seeing is that as we add more powerful instance types in EC2, as we improve the network generation to generation, for example, our recent ENA network adapter, right? Elastic network adapter, enhanced network adapter, you can support these very intense problems high and to the right. Now, when you think about those two spectrums of HPC applications or patterns, grid computing and pleasingly parallel versus tightly coupled, clustered applications. The best way to think about this when running large-scale simulations that require many, many parameter sweeps or many iterations of a job is to think of grids of clusters. So on AWS, a best practice would be, for example, don't launch your entire HPC cluster of many thousands of cores in a single placement group and connect everything together if you don't need to. Instead, take the approach of having multiple placement groups, multiple clusters that are well architected for individual jobs, and now begin to spread those around. Maybe even multiple availability zones, gives us the ability to place them more efficiently, gives you greater access to spot instances, for example, if you do that. That's an important best practice to think about. Build grids of clusters when building high-scale HPC applications. So for simulations, this approach of grids of clusters allows you to vastly increase the simulation domain, right? So now I can run hundreds or even thousands of parallel studies of CFD, or run many, many different Monte Carlo simulations that perhaps are tightly coupled around some data. Spread them around, but keep the use of placement groups and enhanced networking and our most performant EC2 instances for those individual jobs. I just want to walk through a few examples of performance testing that we've done ourselves, that we've done with customers. One thing to note about performance testing for HPC is it's a constantly moving target because we are always, it seems, releasing new instance types. We just announced C5, for example, this morning that will be Skylake-based. So the numbers that I'll show or the graphs that I'll show for performance that may be tested on, let's say, a C4 may be entirely different in 6 months. They just keep getting better, right? We've had excellent success, for example, with weather simulations. And these are traditional legacy workloads like WRF, if you're familiar with the weather modeling environment, that are tightly coupled MPI, message passing interface types of jobs, scaling quite well to many, many cores on AWS. And we do have customers running WRF in particular in production today on AWS. Mechanical simulations, we work quite a lot with ISVs such as ANSYS, for example, to help customers understand how to tune for performance, how to run CFD and mechanical simulations at scale very effectively on AWS. Recently, for example, ANSYS published a blog post, actually back in September, about their testing of AWS EC2 instances, C4 instances, and enhanced networking, using some of the best practices we recommend, and scaling of ANSYS Fluent to many cores, in this case over 2,000 cores on AWS for one of their standard benchmarks, which is 140 million cell mesh, F1 benchmark, F1 car benchmark. So how do you get that kind of performance yourself on AWS? And there's absolutely some best practices to think about, a real checklist of things to think about when you deploy. One thing is when you're doing your own benchmark testing, start with a real-world example, a large example. Don't take a small example or a small micro benchmark and just scale and scale and scale that, because that's not the real world. In the real world, we have very big, meaty problems, right? Large numbers of cells, for example, in a CFD example, big meshes, right? And I'll talk about domain decomposition in a moment, why that's so important to think about in a large problem like CFD or weather. Also think about the instance type. So if you need high clock speeds, lots of core count, C4 today is your best bet. You may, if you need a bit more memory and maybe even more core density per server, think about M4, the largest M4, the 16x large, for example. Absolutely look at our new generations that are announced now, including R4, which is very performant for HPC with high memory, and then C5, which is coming soon. So really think about optimizing your choice of EC2 instances for the specific problem. And that's important to think about if you're familiar with legacy HPC infrastructures. In the legacy world of HPC, you often have a single or a small number of server types that are often overbuilt, over-provisioned, because they need to serve the worst possible application, even though perhaps the majority of those applications being thrown at that cluster could be better served with something else, right? And then think about networking, right? Absolutely, if it's a tightly coupled workload, use placement groups, use enhanced networking, but if you don't need those things, don't use them, because you'll have a better success, for example, using spot instances if you can relax those constraints a bit and not use placement groups. Talk for a moment about domain decomposition. This is a term that's familiar to most HPC customers that are doing things like fluid dynamics simulations and weather. The idea here is that you want to optimize the number of operations that are happening on a given CPU core, right? So maybe in CFD, you want to optimize the mesh in terms of cells per core. Now, every model is going to be different, every solver is going to be different, but there will be a sweet spot. In this case, the sweet spot, the green curve where that's the highest, looks to be around 130,000 cells per core. So that's for this particular model using this particular solver. And if you're looking for the most efficiency, right, meaning the most compute per thread, perhaps because you're paying license fees to your ISV and you want to optimize performance per core, then you might think about that as the best domain decomposition. But that's not always the right thinking in the cloud. For example, if you're running in Spot, incrementally adding lots more CPU cores doesn't really cost you very much. And if you have a code that's not dependent on ISV licenses per thread performance, you might want to push that efficiency curve. So you might want to continue to add more and more cores, even if efficiency starts to drop off. It's a different way of thinking about HPC optimization in the cloud relative to typically what's done in a physical infrastructure. So some other tips, be aware of performance optimizations that you can do at the OS level and in the library level, for example. Make sure if you're using Linux, for example, that you have an up-to-date kernel. Some of the older versions of available OS distributions are not necessarily as performant as they could be. The later generations of RHEL, of CentOS, use Amazon Linux, for example, you'll get the highest performance because those have been tested and optimized for use on AWS. If you have a floating point intensive problem, think about disabling hyperthreading. That can be done fairly easily in the Linux environment, can also be done in Windows. If you do that, you'll get full performance for floating point applications for every thread that you're running on those processors, because one thread will be one processor. That's not always the case, though, and it's easy to try both. Try it with and without. The default behavior in most HPC shops in the on-premise world is to turn off hyperthreading for everything, because you've got a subset of applications that need that, that dedicated core performance. Well, that's not always the case. You may actually find better scalability of some of your solvers with hyperthreading on. All right, so try both ways. You can also optimize through core pinning, through core affinity, using advanced features of the Intel processors, such as P-states and C-states, to actually control turbo. And those are also things that you can do in the EC2 platform today. With respect to libraries, today we do recommend the use of Intel MPI, use a professional MPI library. If you're using OpenMPI, we are working with that community to tune that performance of OpenMPI over time. Today, Intel MPI appears to be the best performing on EC2. And I mentioned hyperthreading before, so it's relatively easy to try it both ways. Try a given solver, threaded or hyperthreaded or not, right? It's an easy experiment to try. Let's drop now into talking about specific instance types and some of the new instance types that we've just announced this morning, actually, that we're quite excited about. So as you know, EC2 has a variety of different instance types that we group into families, and those families range from our inexpensive but quite powerful, actually, T2 instances that have the burst capabilities. Those actually can be used quite effectively for HPC, in particular if you want to have a high burst performance for a short period of time and have a cluster of T2 instances. It can be very cost effective and very performant. M4, that's a general purpose instance type, but increasingly they are being used because they have a good balance of CPU performance and memory for HPC applications. And in particular, the new M4 16X large that's Broadwell based, Intel Broadwell, has very high performance, and it sits on our latest generation network for great performance in a placement group. up to 20 gig performance node to node in those placement groups on M4. We just announced this morning that C5 is coming. That will be Skylake based. You'll get access to things like AVX 512, lots of power in that instance type to come. Today, the workhorses for HPC, of course, would be C4, if you're looking for a Haswell and a relatively high core densities, or M4, as I said before, if you want even more cores and greater RAM per core. We also announced this morning that i3 is coming. NVMe-based storage for a storage head node, for example, or perhaps a data-intensive problem where you've really got to hit that storage with very high IOPS. i3 will be very, very powerful, as i2 is already today. i2, Broadwell-based in the CPUs, high-performance NVMe storage, very powerful platform. Let's move over to the memory optimized for a moment. We just announced this morning that R4 is going generally available now. That provides essentially double the memory that we had in our previous largest R3, up to 488 gig of RAM, and a great balance of performance in the CPU side with the Broadwell processors and that large amount of RAM. So for many applications that are memory intensive, R4 is going to find a great home, right? But let's talk about accelerators. We're really excited about what was announced this morning in the FPGA side. We'll focus a bit on that in a moment. Back in September, we launched our GPU instances, the P2, based on NVIDIA K80. The K80 GPU-based P2s have been very, very popular right out of the gate for applications in HPC, such as engineering simulations, but also things like deep learning training, remote rendering, financial computations, many different use cases for GPU. And sort of as a reminder of what's in an EC2 instance family, EC2 instances are generally provided as different sizes, right? So M4 is an excellent example. Let's just talk about that for a moment. The new M4 16X large is different than the previous generation M4s in that it's Broadwell-based, it has higher performance network, but it has the same balance of RAM and, and compute in that instance. Also in M4, you've noticed that we've moved above 10 gig. We're now at 20 gig in this instance type. And as you'll see with F1 in a moment, we're even moving beyond that with F1 to 30 gig. And we continue to innovate on the network and provide more performance there. And last note about our CPU instances. As you know, we continue to innovate, working closely with Intel to deliver performance across these instance ranges and provide access to those low-level features that you need for HPC, such as control over C states and P states, access to AVX2, and then with C5, AVX 512. All these capabilities provided and visible to you as an HPC user, whether you're an application developer or somebody deploying applications on EC2. Again, with apologies for the speed I'm going through this, we really want to get to the topic now, which is FPGAs and accelerated computing, because we're so excited about this. So we did have, of course, with P2, a GPU-enabled accelerated computing platform that can be programmed using CUDA. It's very, very powerful, very popular across industries and across use cases. And as you've seen this morning, we're not stopping there. We have recently announced, well, actually this morning announced, of course, the F1 FPGA instances. We'll dive a little bit into those in a moment and the use cases and why we're thinking about FPGAs in particular. But today, talking about GPUs for a moment, the K80-based NVIDIA platform, the P2, gives you up to 8 K80 cards. That's 16 GPUs in a single instance type. If you're not familiar with the architecture, those 16 GPUs are connected together on the instance with dedicated PCI Express switching with a fabric. And that allows GPU direct. It allows applications that need GPU to GPU connectivity in the instance to get that kind of performance. A deep learning training, for example, good example of using peer-to-peer connectivity. The GPU instances do support a wide variety of use cases. They're supporting remote rendering for virtual reality. They're supporting financial computations. They're supporting engineering computations. And that's why we chose the K80, because it's got outstanding double precision floating point performance, as well as being a great platform for things like deep learning training. Well, let's talk now about F1. That was announced this morning, and Jeff Barr in his blog posted more information about this today. It is based on Xilinx ultra-scale FPGAs. You get up to 8 FPGAs in a single instance on F1. So the architecture you can think of as being similar to our P2 device, where we've got attached via PCI Express these accelerators, but in this case, they're FPGAs. So what are the different use cases for this? Well, FPGAs are very, very powerful if you have an application that can be massively pipelined. For example, an image processing pipeline, perhaps a genomics pipeline, the ability to stream from computation to computation in a massively parallel way. Another area that FPGAs can really fly is if you need alternative bit widths, right? If you can do computations with 4 bits, 8 bits, 6 bits, 17, right? You can create the data path you need and the computations you need in hardware to get very efficient computation, or perhaps control logic in providing a very complex pipeline that wouldn't be possible in a CPU or a GPU. They're really different use cases, the GPUs and the FPGAs, both very, very powerful for accelerated computing. I talked for a moment about P2. P2 comes in 3 sizes, as you know. The architecture for F1 is similar in that we have multiple sizes. We do have peer-to-peer connectivity that I'll talk about in a moment. In the case of P2, as I mentioned, we do have this peer-to-peer connectivity, the PCI Express fabric on the instance, allowing these GPUs to talk to each other using GPU Direct. So now let's talk about F1. So F1, as I said, has up to 8 FPGAs in a single instance. These are the Xilinx ultra-scale devices. If you're familiar with the ultra-scales, these are the largest, most dense and powerful FPGAs available today from Xilinx. This is the number 2 size, the second largest in that family, the VU9P. It provides up to 2.5 million logic cells in a single FPGA, right? If you're unfamiliar with logic cells are programmable elements that can be used to implement all kinds of different functions, from simple control functions and state machines up to more complex things like math operations and so forth. Configurable using FPGA programming languages like VHDL and Verilog, and synthesized using well-understood tool flows. And more details about that are available now on the AWS website, what that development flow looks like. So some of the use cases I mentioned before, financial computing is actually an excellent use case for FPGAs. The financial community at large has used FPGAs for quite some time for a number of use cases, including high-frequency trading, but also for accelerating analytics and risk simulations and so forth. Genomics is a well-known domain where FPGAs can really shine, as we'll hear in a moment in the Edico case. And certainly accelerated search, contextual search, that sort of thing, big data analytics, FPGAs have actually had a role there as well. And there's many other applications in the video space, in transcoding, image analytics, and so forth. So now to talk more about why FPGAs, what the motivation in there, Peter Van Rooyen from Edico Genome will spend 5 minutes or so talking about what they've been doing historically with FPGAs and where they see the fit now in the cloud with the deployment of their application, Dragon. So Peter.
Thank you, Dave. Is the microphone on? Can you guys hear me? Okay, well, thank you very much, Dave, and really like to just talk briefly about what we do at Edico Genome. What's interesting about genomics, it's really just starting out. Healthcare up to now has been more of a heuristic kind of science, and for the first time, understanding or getting access to our DNA information gives us the opportunity to really personalize medication and to treat some of the really important diseases like cancer in a very fundamental way. So genomics is probably one of the biggest big data kind of applications out there. And it's really just in its infancy. So to give you an idea, one person's whole genome is about 100 plus gig file that gets generated that comes off the sequencing instrument, and that data needs to be analyzed, not just in isolation, but also within the context of a population. And that requires tremendous compute power, and of course associated with that is also the storage of all of this data. Now, the best way to analyze all of this data is to have lots of compute available. And what we've done at Edico, we have developed an FPGA-based solution to analyze all of this data. To give you another idea, this year there will be about a million whole genome equivalents that's available worldwide that's been sequenced. That data doubles every 7 to 8 months. So you can see 5 years, 10 years from now, when every newborn will be sequenced, this data will just really grow tremendously. There's 7 billion people on the planet, and in the next 30 to 40 years, I'm pretty sure most people will get sequenced. So what we're doing is, together with AWS, we're creating a solution to analyze the data, the genomic data, and to tease out the information that's really important within this genomic data for therapeutic use, and also to provide optimal storage for genomic data. So the algorithms that we've developed is, as I mentioned, hardware-based. We've developed an architecture that's scalable, and having a cloud solution together with AWS really provides us the scalability of providing the solution to all the customers and all the genome centers that's out there doing sequencing. So as Dave mentioned, genomics, it's sort of a massively parallel kind of operation in terms of compute to do that. And I think what's important is to just look at the advantage that FPGAs have relative to just doing it in CPUs. Up to now, if you were to do the analysis of one genome, if you do that in software, it's about a 15, 20-hour kind of process to analyze the data. We have an on-site solution today in FPGAs. We bring that time down to about 22 minutes. With this powerful AWS solution, we can do it literally, virtually in real time. So something that took 15, 20 hours to analyze and to really understand what a genome is all about, and to provide therapeutic guidance based on somebody's genome, we bring that down to essentially real time with this AWS platform. So it has really significant implications to all of us and all of our families, and it's just really an unbelievably scalable way of addressing this particular issue. Now, what's also really important about that, being able to do this in almost real time, apart from the diagnostic and therapeutic applications that come from that, it's also that the cost scales linearly relative to the time that's required to do the analysis. So as you know, you rent instances in the cloud, and if you can do the processing in, let's say, 1 minute versus 10 hours, the cost will be significantly reduced. And that's really what we provide, and Dave, together with AWS and this platform, we look forward to providing an unprecedented service to customers, to our customers, to AWS's customers, and to help everybody get to that dream of personalized medication in the near future. So thank you very much, and we look forward to working further with AWS.
Thank you, Peter. How's that? Excellent. So as I described before, and as Peter just mentioned, genomics is well understood to be acceleratable in hardware Research has been going on for quite some time. There's been real-world deployments, such as Edico, showing dramatic throughput improvements. And this is possible because you can bring the data right next to the hardware pipeline that's processing it. So you'll see in the F1, for example, there's a large amount of DDR4 that's closely coupled to the FPGA instances with multiple memory interfaces. This provides all kinds of unique opportunities to accelerate data processing of all sorts, right? So data mining, analytics on images and video and text and so forth. Many, many applications. And we can't even envision at this point what other interesting applications will land on the FPGA accelerated F1 instances, because this is really quite new for the cloud today. So if you've got great ideas, it's easy to get started. We do provide a development kit, a hardware development kit, an HDK for the F1s. It does require a little bit of hardware engineering savvy, but we do help with that by providing the interfaces, all pre-developed and pre-configured, so you can just focus on the application, on the algorithm to deploy into that FPGA. Super excited about it. Oops, I'll just use this. So let's talk now about deployments. Let's kind of talk about the big picture of how you deploy HPC on AWS. It's a very important topic because HPC often comes with it a lot of legacy, right? If you're an enterprise customer that's been doing HPC for big simulations, or perhaps in the genomics space or the animation rendering space, there are patterns that have developed over many, many years that are very efficient for an on-premise environment, but may require a little bit of rethinking in a cloud environment when you have the opportunity to scale up so dramatically. I'll talk about that traditional pattern for a moment now. So in a traditional environment with HPC, these are the major components that you might see in an HPC data center. Starting from the top, you often have the need to do remote login, to do, let's say, pre and post processing, to do visualizations, maybe to do some design work up front, run the simulation, look at the results on the back end. Those are typically graphical applications, right? So increasingly, the use of remote desktop is very important there, and there's a number of solutions that customers deploy for on-premise use of remote desktop and visualization. The second thing down, in a typical HPC environment on-premise, you're going to have some persistent nodes that maybe they're cluster head nodes, maybe they're license managers, right? They're just sitting there doing basic housekeeping, right, for the cluster, submitting jobs to the stack, taking care of users, priorities and so forth, managing those licenses. And then you've got the cluster itself, the third box down. So in most HPC shops, that cluster is quite large. It may consist of multiple generations of servers because perhaps you refresh every year and a half, 2 years, and you're constantly rolling in new hardware. It may or may not be optimized for specific applications. So if you're an HPC shop in manufacturing, you probably have dozens, maybe even 100 different solvers and CAE tools that you need to run in this shared cluster. And so you have to build a cluster or a small number of clusters that can support that mix of applications as efficiently as possible. So it may be overbuilt in terms of network, in terms of memory, in terms of CPU core performance and so forth. And you're, as I said, constantly refreshing that and adding new capacity to keep up with your changing needs. But day to day, it doesn't really change size, right? And also in most HPC shops today, again, whether you're a semiconductor company, you're an animation rendering shop, you're doing financial computing, these types of applications, genomics, you often have the need for high-performance storage, right? So many applications out there today really do rely on, because of their legacy architectures, a large amount of high-performance shared storage, right? So how do you now migrate these to the cloud? How do you move these to the cloud? Well, the first thing to think about is just kind of lift and shift. Can I recreate that legacy HPC cluster in a cloud environment? And the answer is yes, you can, and you'll get some advantages in doing that for sure. One of the biggest advantages you'll get, of course, is that you can automatically scale up and down the cluster in response to need. So perhaps I can instrument the job queue if I'm running Torque, or I'm running a SunGrid engine or some scheduling environment. I can now instrument the job queue And if there's more jobs submitted to the queue, I can automatically add servers. I can auto-scale up and then auto-scale down when the queue drains out. And that's a great advantage right there in terms of efficiency and getting fast time to results, because you no longer have that queue contention and queue wait time that you suffered with in the on-premise environment. Another advantage, of course, is that you can continually refresh. So it takes a few lines of code or maybe a few clicks just to refresh, let's say, from C4s and M4s into the new R4s and C5s as they come along. You don't have to wait for a refresh cycle to get access to these new capabilities. And maybe you want to broaden that out, and you'll start to have distinct clusters that look like this for distinct applications. Maybe a GPU-accelerated cluster that comes and goes, and another one that's CPU-oriented, maybe an FPGA cluster, right? You can start to think about segregating different clusters for different workloads. On the storage side, you can absolutely create a shared file system on AWS. There's lots of ways to do that. You can use EFS. You can use something like Intel Lustre or some other file system. And this file system architecture you choose will depend to a great deal on the applications. Is it small file and IOPS intensive? Is it primarily read of larger files? These will really help you to think about what shared file system you need. But increasingly, you want to think about how can I reduce the dependency on shared file systems? I'll talk about that in a moment. Up at the top, for remote graphics, you can absolutely use the cloud for remote graphics for pre and post processing, in part because we have our G2 GPU instances, but now also because we have just announced our Elastic Graphics offering. It will be very, very useful for end users as well as for ISVs that are supporting those end users with graphics-oriented HPC solvers. So we're really excited about Elastic Graphics for HPC customers. And then finally, your license managers, your use of head nodes and so forth. Really, it's the same in the cloud. It doesn't matter to let's say, your Flexera license server, whether it's running back on premise and communicating to the cloud or running in the cloud on an EC2 instance. It's really the same model. Works just fine, right? Now, this may or may not be the most optimal. I want to talk about how to rethink HPC clusters in the cloud. So the first thing you might think about if you have a legacy architecture, and this is just another way of drawing that legacy architecture, is to start adopting additional EC2 or AWS capabilities because they're there, right? So in this case, we've got a hybrid environment like I just described. On the left side is our existing on-premise HPC infrastructure. In this case, this would be a financial services company running grid simulations. On the right, we've got our automatically scaling, auto-scaling cluster that is observing the job queues, right? So maybe I'm running a scheduler of some kind. I can instrument that job queue. I can scale up, scale down, use spot instances. I can stand up, if I want to, a shared file system. If I want to, I can use managed databases and so forth. I can begin to deploy in the cloud something very similar to what I was doing on premise, but now it's more flexible. But now you can think about doing even more things, right? So here, for example, we're saying, well, what about the job logs? How about if we take the job logs that are coming out of my HPC cluster and let's push those into some analytics platform? In this case, we're doing a fairly simple batch environment. We're pushing them initially into DynamoDB, then we're going to push them into Elastic MapReduce. Now we're going to do some analytics on job logs. So why would we do that? Well, maybe we want to analyze our users' behavior. Maybe I want to identify if we have some internal customers who are accessing the grid and maybe stuffing the queue with jobs that don't need to be there, or just find out, what kinds of workloads are dominating. Do we need to think about alternative architectures on the cluster side, on the grid side? You get a lot of analytics just by looking at job logs in an HPC environment, and that's not necessarily easy to do on premise because you'd have to stand up some kind of analytics platform, but it's super easy to do in the cloud. But let's take it a little bit further. How about if we just rethink what HPC should look like? Now, this use case actually comes from the semiconductor sector. Now, Amazon ourselves, we develop chips. We're a semiconductor company. We have semiconductor customers. This is increasingly a kind of a pattern that's interesting to these customers. So what we're trying to do here is get away from having that single managed cluster that I described before that handles all of the different workloads used in electronic design automation, in semiconductor design. So at its simplest, what we've done here is we've at least segregated into two separate clusters that are going to scale up and scale down individually. Each one of these clusters itself has clusters within it that are optimized for particular applications. And we've just sort of made some up here, right? We're not really saying exactly what these workloads are. But on the left side, let's imagine that AZA, and they don't have to be segregated into different AZs, by the way. But let's imagine AZA is a design center. So that's where the folks that are doing the actual engineering of what goes in the chip are going to work. So they're running, RTL simulations, if you're familiar with the term. They're interacting with simulators. They need remote desktop, and so they have that in that cluster in a controlled way. They have access control. We know exactly who's using those, how they're using them, what kind of IP, intellectual property they're integrating with, right? Whereas on the other side, we've just got it in AZB, but again, it doesn't have to be different AZs. We've got a separate cluster that's used for that back-end verification of the chip. So that's where we're doing regression testing, we're doing mask verification, we're doing those things on the back end that are more related to producing the chip. Now, maybe for security reasons, we like to do this because we don't actually want the developers of the chip on the front end who are developing that IP, that intellectual property, to have access to the back end. Because maybe we don't want a bad actor on the front end to have access to insert something in the back end that doesn't belong there. We want to really segregate these functions out. Or maybe we want to collaborate with different third-party partners. Maybe an IP provider on the left side, maybe our foundry partner on the right side. And this segregation, the ability to easily create multiple chambers, if you will, in a cloud-based environment can be very, very powerful for HPC customers that are very security conscious and that also need to collaborate with third-party partners. Now, one of the things that we've done here is we dramatically reduced the dependency on shared file systems. You won't see one great big shared file system sharing NFS to all of these different servers. So as part of the optimization process, you want to look application by application. Do you really need that very large high-performance shared file system, or can you start to unwrap that, right? Application by application, that process will be different, but it's a very important optimization to think about. In particular, if you have applications such as regression tests where you could conceivably package up the data with the job deck, submit it, and not hit shared file systems all the time. Much more efficient if you can just communicate with S3, that's your primary source of storage. Rethink HPC using the capabilities in the cloud for storage management and for automation. And we do have capabilities that can help with this. HPC customers today that are standing up almost replicas of what they're doing on premise and then extending them further are increasingly using CloudFormation to do this and using some of the templates that we provide, in particular CFN cluster. I don't have time to go through all of the capabilities of a CFN cluster. It's an open source project. It's accessible on AWS in the HPC portion. Just search for CFN cluster, HPC, you'll find it. Again, you can download that. It's open source. You can modify it, change the file systems, change how the schedulers operate with it. But this helps you to integrate traditional legacy schedulers used in HPC with an auto-scaling, optimized environment on the cloud for HPC. It's been very, very, very popular in life sciences, manufacturing, and other domains. Quick note about storage, right? So I mentioned before the reliance on shared file systems is common in HPC, and you can absolutely use that pattern on the cloud. You could, for example, on the left side, you could use EFS, right, to be your file system. That can be very powerful if you need a lot of read performance, if you just need the scalability and durability of a shared file system. If you need very high performance, high IOPS, right, the traditional semiconductor is a great use case, right? Regression testing really slams a file system with high IOPS. And so you may prefer then to deploy something like Intel Lustre or your own shared file system implementation using a collection of EC2 instances in combination with a well-architected use of Elastic Block Store, EBS. So you can create a shared file system that's well-tuned for your particular application. It's best to think of that file system, though, as ephemeral. as something that you're only using during the course of the job run. Your source of truth, the place that you should really store the data long-term and persistent, would be S3, an object store. The more you can take advantage of object store, the more you'll have cost savings, but you'll also have high performance, because the throughput that you can get from S3 into your instances is extremely high, including instances that maybe are sharing or they're supporting a shared file system, right? So a well-architected HPC infrastructure on AWS will be a combination of S3, where the bulk of your data lives, life cycling out to Glacier for cost benefits, and then when you need it hot for the course of a run, then move it into a shared file system, typically built using EC2 and EBS or using EFS, right? So think of those different tiers of storage when optimizing an HPC infrastructure. The graphics I mentioned before, very powerful capabilities for remote graphics today on the cloud, and it's only getting better. Again, we heard this morning about elastic graphics coming soon. The ability to use GPUs in the cloud and deliver only pixels is very powerful for cost savings, for efficiency, but it's also very powerful for securing your HPC environment. Only push the pixels to the end users that are doing that front-end design or that are doing that visualization, or perhaps your collaborators at a third-party organization. Use remote graphics to do that. Earlier this year, we acquired NICE software, who provides the DCV capability, which is widely used in some sectors of manufacturing and automotive, et cetera, for remote desktop. And we are moving forward with that technology. It is core to what we're doing, and today very well supported on AWS for delivering that remote collaboration and graphics environment. I'll talk briefly about software licensing. When we talk to enterprise HPC customers, this is often a question that comes up, and it's very important to engage with your ISV partners on this topic. But I want to at least characterize what some of the options are for licensing software that's used in the HPC community, whether it's engineering software or other software that's perhaps used as middleware in support of that software. There's two basic ways to think about software licensing on the cloud. The first way, let's just characterize as customer managed, right? So you really want to do the same thing that you're doing today on premise, manage the licenses yourself, negotiate with the vendor yourself, deploy it yourself on your infrastructure. And that works the same, of course, in the cloud. You may have to get clarification from your ISV as to what the regional implications are. There are certainly ISVs out there that have legacy license terms that refer to geographic locations and so forth. You need clarification what it means if you're deploying that in an AWS region that's perhaps not within, let's say, 100 kilometers of your site, right? So that's very important to get clarification. But once you have that, the deployment is very, very similar. You can put the license server, for example, on premise and point it out to the cloud, right? Using either direct connect or VPN, extend your network out. The license server doesn't really know the difference. Or you might want to put the license server itself out in the cloud as part of a complete HPC infrastructure. Either works just fine. The other option, of course, is software as a service or some sort of managed service. And I'll have examples in a few moments of what that might look like. So maybe you want the ISV to handle all of the infrastructure, to take care of standing up the cluster and managing those jobs. You just want to access the solvers, access the visualizations and so forth using a service that they provide. That's, of course, software as a service. There's numerous examples of that today on AWS. And of course, it's a widely understood and used model across industries, right? I'll give you two examples, right? So ANSYS, a very, very popular provider of engineering software, really every kind of simulation you can imagine. They deliver from electromagnetics to fluid dynamics, lots and lots of solvers. What ANSYS provides with ANSYS Enterprise Cloud is actually the first model, helping customers self-deploy on AWS, on the cloud, right? So the customer has an account with AWS, manages the infrastructure, ANSYS Enterprise Cloud is installed into that. And the ANSYS Enterprise Cloud, the automation they provide, makes it very easy, really automatic, to stand up the automatically scaling cluster, stand up the file system, set up the remote graphics. It all just sort of works out of the box, but in your environment, in your virtual private cloud. So that's one approach that's very, very popular and very convenient for customers, again, to run in their own accounts. Another example might be Altair providing their Hyperworks Unlimited. Now, Hyperworks Unlimited, they're providing more as a software as a service. It's very convenient. You just go to a portal, you log in, get your credentials. You're running in an Altair managed account on the cloud, and you just run the solvers and use it. Both models are completely legitimate, supported, different use cases for each. It really depends on your organization needs. From an infrastructure perspective, either one's fine by us. And you're running on the cloud, it's secure. In this case, you're letting the ISV do all of that sort of heavy lifting of infrastructure. In the case of ANSYS, they're also helping you with that heavy lifting. It's just in your account, right? So both approaches are completely appropriate. You can also make use of managed service providers. Cycle computing is an excellent example here. And cycle computing actually enables the work I described earlier with HGST and other customers. So they are helping customers to do that management in the customer's account. So they'll come in, they'll help them set it up, help them take advantage of spot instances and cost optimize and all those things. So there's a growing community of consultants out there that have perhaps some technologies to help with this, some expertise that can help to manage an HPC infrastructure and that migration into the cloud. Another example that's more of a software as a service would be Rescale. So Rescale provides a portal where you go to the Rescale site, you get an account, you log in, and now you have access to lots of different CAE tools that they are providing in more of a software as a service environment. So if you need to use, for example, CD Adapco Star CCM and use it for 6 hours or a month, they have a way to do that, right? You can just pay by the hour or pay for shorter term use of those solvers in a managed environment. It's very, very convenient for running project-oriented workloads, for getting something done quickly. Rather than managing your own infrastructure, you go to Rescale. They've already worked it out with CD Adapco or other vendors to provide that solver for you under the very easy pay-per-use kinds of terms. And they've got many examples across industries. In automotive and engineering, in this case in the manufacturing sector, boiling oil is an interesting use case, right? So lots and lots of examples like this out there. HPC is actually being used in so many domains now, in part because of cloud is making this possible, that users that previously had very little access to HPC capabilities, Trek Bikes, for example, is a Rescale customer, that previously getting access to simulations at the scale they can do now were very difficult. Now they're becoming very, very easy. Another example over in Europe, ANSYS Flight, also taking a wide variety of different open source and commercial solvers, packaging those up, making them easy to use through a portal online, right? There's just many more examples of this available in AWS Marketplace and among our partner network. I did want to mention one additional partner, and what you can now think of in the future of HPC is a microservice-oriented approach to HPC. I can't really do them justice by just talking about them. It's best just to go to algorithmia.com and try what they do. What they provide is a marketplace of algorithms. And many of these algorithms are things like deep learning inference. They are image processing algorithms. Much of the same way that we have Lambda to provide smaller, more granular functionality, Algorithmia provides this for deep learning, for HPC applications. It's a very interesting approach to think about, getting away from even thinking about servers and infrastructure and assembling high-performance applications using a microservice approach, API-accessed functions. One example in the case of Algorithmia, if you're doing an image processing pipeline and you need to identify objects in a video stream or sentiment analysis, that sort of thing. One of those examples is actually like nudity detection, right? Very important for some domains to make sure that content is properly filtered. Accessing those independent functions through APIs and let someone like Algorithmia worry about the HPC infrastructure under the hood, in their case, GPUs, right? It's a very interesting approach. I think we'll see more of this over time, in particular as we have software partners who are very good, or experts perhaps, at using accelerated computing environments like GPUs and FPGAs, or have specific applications and algorithms that could be deployed across different use cases, across different applications. So that was a lot of information, and we're just super excited about what's happening in high-performance computing on AWS, in the instance types, in the networking, and accelerated computing and automation. We do have other sessions that we certainly welcome you to join. The example I just mentioned with Algorithmia, they have a session, I believe it's tomorrow, CMP314. There's much more information about our P2 and F1 FPGA instances in the CMP317 session. It doesn't say FPGA in the title because that was embargoed until today, but there's a fair amount of FPGA content in that second one there. And other examples, building HPC clusters as code, and then elastic graphics will be covered in the delivering graphical applications on AWS. So thank you for your time today. I really enjoyed the session, and we'll stay here for questions for the next 15 minutes or so. Thank you.